So welcome back, everybody. This is Night Flight, and today Ralph Ellis is back. And yeah, we are going to talk about weather and climate. And I'm pretty sure it will be a very, very interesting show. So welcome, Ralph.
Oh, glad to be back again, Judith. Yes, good to be on your show again. Yes, it's going to be interesting because, as ever, the data I have is not the same as we have been told and given. So it's going to be all very different to the mainstream media view of climate. And because everything was not as advertised, that's why I made my peer review paper. So I made this climate paper, which sort of demonstrates that CO2 is not the main problem. That
Mhm.
was not the task. It was a paper about ice ages, but it sort of proves that CO2 is not a major player in climate.
Mhm.
So
Can we read that paper online?
yes, it's called. I'll give you the. Let me do a share screen and bring it up. So OA modulation must be that one, I think. There we go. If I share that screen. Okay, so that should come up with the faceplate of my paper, which is Modulation of Ice Ages by Dust-albedo Feedbacks, which is a proper peer-reviewed paper. It's a proper science paper, been through university and had peer review by 5 reviewers, no less. And yep, they all said it's makes sense. Of course, peer review doesn't say it's true. It just says that it makes sense and it's a good paper. Trying to explain how ice ages happen because nobody knows or nobody knew how ice ages happen. And so this paper explains it. But the and it's free online because most papers you have to pay for. It's like 50 euros or something per paper.
Yeah.
But this one is free because we got it. The university paid for it to be put online, so that's good. But the reason I went down this road is because the data, the real data, the weather data, the climate data, is not as advertised. And so, because of that, I started researching climate. And I was researching climate with, it was basically on what's up with that. But we had Leif Svalgaard on there, who was a um, astronomer more than a climate scientist. And he was going into the orbital mechanics of ice age modulation, which didn't make sense. He could not make it make sense. Nobody could understand what he was talking about because there was a big hole in it, which we will see why there's a big hole. And so I started looking deeper and deeper into this. And the climate data did not add up as well. So if we look at this, we're going to be looking at CO2. The reason that CO2 becomes important in my paper is because it's plant food.
Yeah.
Now, a lot of people still don't know that it's the most important gas in the atmosphere. The EPA in America actually branded it as a pollutant, but of course, it's the most important gas in the atmosphere. Without CO2, everything dies. And this is just a quick illustration of that. So on the top, we've got rice, which is a C3 plant. And the more CO2, so at the bottom here, we've got CO2. The more CO2, the bigger the growth of the plants. The less CO2, the plants die. And they normally say anything below 150 parts per million, and the plants will die. And that's almost what we came down to during the last ice age.
Mhm.
CO2 dropped almost to nothing. And we'll see that in a minute. So CO2 is important.
Yeah, I know
Uh,
that farmers, for instance, when they have greenhouses and the plants are not growing as they would like it, then they add CO2 into the greenhouse.
They do. So it's I'm just going to make my cursor a little bit bigger. Um, if you're running a greenhouse, what they'll often do is pump extra CO2 into the greenhouse.
Mm.
So, and I was debating even recently with someone who was supposed to be knowledgeable, and they said, "Oh, you can't grow plants above 800 parts per million because it becomes toxic and it's bad for the plants, and it's the plants you get are not so good if you have higher CO2." And I said, "Well, yeah, but most greenhouses run at 1,200 parts per million,
Mm.
3 times more than we've got now in the atmosphere in order to make the plants grow faster." And that's what you're eating now. If you're eating tomatoes and cucumbers and things of this nature, things that are grown in greenhouses in Holland, for instance, where they grow a lot of this stuff. So CO2 is essential. The other thing we need to know is that CO2 in the past used to be much higher. So on this little graph, this goes back 400 million years. So this is a big long-term graph. The purple is the CO2. And we're down here on the right-hand side at present, and you see very, very low CO2. Back in the Jurassic era, when we had all the big dinosaurs, CO2 was up at 2,500 parts per million, 6 times higher than now.
How did
Uh,
you find that out?
well, they find it out through proxies, they call it. So you can find it out through mineral composition when you
Ah,
core
okay. Mm.
things like stalactites, stalagmites, and going down, coring the ground. And also, if you pick up coal deposits and the coal has fossils in it, fossils of plant leaves, you can count the stomata. So the stomata are the little mouths on the bottom of the leaves through which the leaf breathes. And the more stomata, the less CO2 in the atmosphere, because the plant needs a certain amount of CO2 to grow because it is plant food. If there's lots of CO2 in the atmosphere, then you don't need very many stomata. So there's a direct correlation between the number of little holes in the bottom of the leaf, the stomata, and the amount of CO2. So all you need to do, it's fairly simple, count out the number of stomata, and you'll find out how much CO2 there was in the atmosphere when that plant was growing. And that's another way you can demonstrate how much CO2 there used to be. But the thing to note is that during the Jurassic era, 2,500 parts per million, the biosphere was fine, no problem at all. In fact, the giant size of the dinosaurs was due in part on extra CO2.
Mhm.
Because more CO2 equals bigger plants, equals bigger herbivores, equals bigger carnivores. That was, part of the reason for the dinosaur era. So all of these dire, shrill um, uh, warnings from the likes of, Greta the Gremlin, um, that, if we go beyond 500 parts per million, the world will die, everything will die. It's nonsense. Back in the Jurassic era, it was 6 times higher. Again, with the corals, the corals will die because of too much CO2. Sorry, the corals have been living for 500 million years. They lived when CO2 was up at 4,000 parts per million, and the corals were fine. So yeah, don't tell us that the corals are going to die because of extra CO2. They've been through it all. They've seen it all. Um, and sometimes very, very rapid changes as well. It's not just, static. So on this graph, then the purple line is CO2, the blue line is temperature. And as you see, there's not much of a correlation between temperature and CO2. It's
Mm.
a good indication that maybe CO2 is not controlling temperature to the extent that the alarmists like to say. And then in the Holocene, which is our recent era, so this is going back 11,000 years, temperatures again were much higher than now. So again, this alarmism that, oh, if temperatures go up 2 degrees, everything will die. No, it was more than 2 degrees warmer back in the Holocene. That was only 8,000 years ago. So on this one, the temperature is this black line at the top. 11,000 years is here, 11,000 years ago. And so the temperature goes up, up, up in the, because this was the ice age here, 12,000 years ago was the ice age. Then it started to warm and it goes up to the very top, and then it's been coming down ever since. So we are much colder than the peak of the Holocene. They call it the Holocene maximum. The Holocene maximum, when the Sahara Desert turned green and fertile with rivers and lakes and hippopotamuses and God knows what, that was 8,000 years ago. And we've been cooling ever since. And then you come to our recent era, and they've got this little tick up here, of course, because it's got a little bit warmer, but nowhere near as warm as during the Holocene maximum. So again, this alarmism, the little bit of extra warming is going to, kill everything, is nonsense. The biosphere is very robust, and it will survive temperature changes. And again, you see no correlation. CO2 is in red here, going up. No correlation at all between temperature and CO2. Or methane, for that matter. We've got this new scare. They like a new scare, every now and then they bring something out, just to keep you on your toes. Oh, it's the cows now. Never mind the coal and everything else. Part of the reason they said that is because now Germany is burning more coal than they ever did before, because some nutter closed down all of your nuclear power stations. So it's very awkward to say, oh, CO2 is bad now because they've just opened up all the coal-fired power stations again. So now they're saying, oh, methane, it's methane. We've got to get rid of the cows. Well, there's not much correlation here between methane and temperature either. So methane is in blue, and the temperature is in black here. No correlation at all. How do we know it was warmer during the Holocene? If I go backwards, so that's the Holocene. Well, they do it by tree lines. Is one of the best ways to know the temperature. So this is the north. This is going up into the taiga, north of Siberia, going up to the Arctic Ocean. And so this is sea up here. This is land down here. And today's tree line is this dotted line here. That's the tree line today for this particular tree, which is called betula, whatever that is. Don't know what that is. Some sort of pine, I'm sure. But 8,000 years ago, this was the tree line here where it's shaded. That was the tree line. It's 200 kilometers further north. And the only reason the trees could grow that far north is because the temperature was much warmer, so they can decide how warm it was. Some of these papers say that it was up to 7 degrees centigrade warmer 8,000 years ago during the Holocene maximum. So we're nowhere near the temperatures we reached during the Holocene. The diagram down the bottom is the same, but it's for a different tree. That's for the larix, whatever a larix is, another pine tree, I'm sure. And again, the modern tree line is down here with the dotted line, and the ancient tree line is the shaded area, and that's about 100 kilometers further north. So we know it was warmer during the Holocene. And that does the same. It's just another graph doing the same. This is just a graph of the Holocene. This is a temperature graph from 20,000 years ago to the current time. Temperatures on the left as a, that's probably a temperature of the Arctic. That's why it's in negative, because it's measured up in the Arctic. And so here we have the end of the ice age. We had this very sudden warming. We call it an interglacial. And then we had the Younger Dryas. So we had this sudden cool period for 1,000 years, which nobody still quite knows why we had this sudden cool period. A lot of people, myself included, think it was a meteorite strike. There is evidence in America that there was a meteorite strike onto the ice sheets. Anyway, for whatever reason, it suddenly went cold again, and then it got warmer and warmer into the Holocene, maximum temperatures here, and then it's been cooling ever since. So yeah, that's the Holocene. Another way they measure these temperatures is by tree rings. I suppose for tree rings, the max we can go back is 1,000, 1,500 years, something like that. Anyway, I don't like tree rings. I think this is snake oil science. It's not real science at all. It's pseudoscience. What they do is they measure the tree rings to see how big they are, and the bigger the tree ring, the warmer it is. But that has so many holes in it, as a science. I mean, what makes a tree grow? Nutrients, canopy cover, water, amount of precipitation, maybe heat, but I wouldn't put that first. I might put that, second or third. I think the main thing is how much water you get. If you have a very dry summer, it'll be very hot, but the trees aren't going to grow if you don't have enough water. So I would think that tree rings are measuring precipitation more than they are measuring temperature. And the other problem is when they core it, they core about 1 centimeter diameter. They put a core into the tree and measure the tree rings. But here, if you put the core down here in the 7 o'clock position, it'll be very warm. But if you put that same core in the 3 o'clock position, it'll say it's cold. So was it hot or was it cold? You see the problems with their measuring techniques on these. I mean, it's just, to me, it's a complete nonsense, the whole thing. And it's a nonsense in the data as well. We've had a lot of this that I've been looking at. Some of the best people to look at this is John Christie, Professor John Christie, McKintrick and McIntyre in Canada. They're not even climate scientists. They are statisticians working in the oil industry, for which, of course, they say, oh, look, working in the oil industry. But they're statisticians. And, of course, most of this science is statistics. That's how they work out, these graphs. And they've proven that a lot of these graphs are highly suspicious. So this is tree ring data. This is Mushkin Piggy, they call it, which is an area where they took these trees from. They measured the trees, they got the tree rings, they got all the data, and this is the data. So this is the raw data going back 500 years. Today on the right, 500, 600 years ago on the left. And the bigger the tree ring going upwards here, the warmer it was. Yeah, so it gets warmer and warmer and warmer, and then it gets colder for the last 200 years. So that's the raw data. Then they have to do this processing of the data. So they take this data, and after they've processed it, it looks like this. Yeah, so suddenly they've managed to make it warming. So they turned cooling into warming via their processing. This is why a lot of people think that this is just poor methodology, or fraud, you might call it, but let's call it poor methodology. And then this is another one. This is tree rings again. This was, what was his name? I can't remember his name for a minute. Anyway, I'll remember a minute. Briffa is his name. This is a tree ring series going back 600 years again. And it does not much at all, really. It just bobbles up and down a little bit. And then when we get to 1950, it starts cooling. It starts going down. This is what they called hiding the decline, because it was actually cooling after 1950. But anyway, then they process the data. You've got to process data. You can't just give raw data. So they process the data, and then it looks like this. So they turned the cooling into warming. It's clever. They call this um, the uncertainty problem. No, what do they call it? Anyway, they've made a special term within climate scientists um, that tree rings record temperature precisely for 1,000 years until you get to 1950, and then they stop recording temperature. And this is a thing, really, in the divergence problem. That's what they call it in climate scientists, in climate science. That tree rings give the correct temperature until 1950, and then they stop. And so after 1950,
So
you
the
have
trees colluded together and
yes.
and don't give away any data. Okay.
And they won't explain why the trees suddenly don't record temperature after 1950. But anyway, after 1950, they have to put in the thermometer data. And that gives us the hockey stick graph. That's why it's red on the end. It's actually a splice of two temperature data sets. I would tend to call that fraud, but there we go. And we have this from their emails. So this is one of the emails. This is one of the ClimateGate emails that was stolen out of the CRU in East Anglia, one of our climate institutions. So this is an email from Phil Jones to Ray Bradley and Michael Mann and Keith Briver. These are all climate scientists. And he says here, I've just completed Mike's nature trick. So Mike is Professor Michael Mann. Nature Trick is the science magazine Nature. And the trick is manipulating the data, of course. Mm. So I've just completed Mike's nature trick of adding in the real temperatures for each series for the last 20 years, from 1981 onwards and from 1961 for Keith Briver's data in order to hide the decline. So they're doing it deliberately. There was a decline in temperature. According to the tree rings, the temperature went down after 1950. So what did they do? They chopped the end of the data off at 1950 and stuck the thermometer data in there instead.
Do you have any idea what their motivation is for doing that?
Money.
Oh, okay.
Fame and money. Because the whole thing they were tasked to do by the emerging IPCC was to go and find warming, because that was the that was the scare, that we were going into a warming era. And so they had to find warming. Well, there's no point doing all of this research if you suddenly find cooling. You don't get any more grants if you find cooling. So you've got to find warming somehow. And that's what they found. And as a side product to that, they found fame and fortune as well. You know, because the CRU in East Anglia used to be a couple of mud huts. Now it's an entire institution. Now it controls trillions of dollars of public money, spending on all of these conferences, you know, jet setting across the world. You know, the last COP conference that I think something like, it was something really daft, like 500 aircraft turned up. I mean, it was just an enormous number of people. Britain ourselves, we sent 400 people. Why? 400 people for doing what? Oh, they're just having a good time, aren't they? This is it's not climate science anymore. It's just people on the gravy train. They've jumped on this very, very lucrative bandwagon. There are literally not billions of dollars being spent on this, but trillions. If you can imagine all of the work now that's going into wind turbines and solar and all of the energy transfer that we're doing now, as well as all the science and the satellites and everything else they're putting up, this is trillions of dollars. So a lot of people have made a lot of money out of this. It's big climate, or big green, you might call it, is now bigger than big oil. You know, everyone used to complain about big oil having too much influence. Well, big climate is much, much bigger than big oil now in terms of its revenue. And because of that, they have to keep the gravy train going. But they're doing it by giving you duff data. And this is the reason I got into this, was because the data did not match. Because we all know what the problem is. The climate's getting worse. That's why we've got this change in our energy policy, because the world's going to end in 5 years. Well,
Yeah, yeah. Since 1970.
yes, that's right. Well, Greta the Gremlin said that in 2015, I think it was. She said the world will end in 5 years. Well, that was like 4 years ago now. And they keep saying this, as you say, every 5 years they say it. But when I looked up the data, that's not what it said. And this was many years ago. I wrote about this. I think the first paper I wrote about this was 2004, which was called Renewable Energy, Our Downfall.
Mhm.
Because even then, back in 2004, I was saying that renewable energy will not cut it. It will not do what we want, which is to keep us, with sufficient energy. As a part of that, I was looking up the climate data, and that was not as advertised. So, for instance, with tornadoes in America, we all know that they're getting worse. They're wiping out towns and cities all over America. Because the weather is getting worse. And then you look up the data and you find that number of strong tornadoes in America has been going down for 70 years, and significantly down as well. And this is all real data. I'm not making this up. This comes from NOAA, NOAA NCDC. So you can look it up. In fact, you can't look it up anymore, because they used to make a graph every year in NOAA, just like this. And then they stopped because the graph was going the wrong way. There were less and less tornadoes. So what they do now is they publish the data. So you've actually got to download the data and make your own graph, which is a real pain, but there we go. You just put it into a graphical software suite. The reason they are tracking strong tornadoes is because the strong tornadoes were the ones that were tracked even going back into the 1960s. The problem nowadays is you can't add in F1 and F2 tornadoes, because the new weather radars will pick up every single tornado there is, which wasn't happening in the 60s. So the only ones we can track for sure since the 1960s are the strong ones, F3 to F5. And they have been going down for 70 years. Same with hurricanes. We all know what's happening to hurricanes, that global warming is making the weather worse, and we're getting more hurricanes, and they're worse, stronger, and they're destroying entire nations just like that, washing them away. Well, the data actually says the opposite. So this is Chand et al. This is only 2022, so it's only 2 years ago, this one. And this is proxy data of global TC, tropical cyclones. So this is the whole world, not just hurricanes, it's typhoons as well. And they went up from 1850 to 1900, and then they've been decreasing for 120 years. Not by much, but I mean, from 100, about 20%, something like that.
Mm.
They've been going down, totally the opposite of what people have been saying. Now, this is proxy data. Some people don't like proxy data, so let's look at the satellite data. Unfortunately, satellite data is only recent. It's only from 1980, but this is the satellite data. This is by Professor Mao and Ryan Mao. I think he's in Honolulu, I think. Anyway, it doesn't matter where he's based. This is satellite data from 1972, and this is accumulated cyclone energy, so the total energy of cyclones every year. I think it's actually calculated on a month-by-month basis. Anyway, so what have we got here? Global on the top and Northern Hemisphere on the bottom. Most hurricanes are in the Northern Hemisphere. We have very few of them in the South because there's no land masses. It's the land masses and the differences in temperatures that causes the hurricanes. But anyway, they went up from 1972 up to 1996, roughly, and then they've been going down ever since. Okay, not a big change, but from, on this scale, 1250 to 1600 and then back down again. In terms of numbers, again, this is from 1980. Major hurricanes on the bottom, all hurricanes on the top. So all hurricanes have been decreasing very slightly from 48 to 43. It's still going down. And major hurricanes, steady, no change. So where is the climate emergency in this data? It's just not there. And we can take this back further because the one I like to use is American landfall hurricanes. Because again, this one we can only go back to 1980. Landfall hurricanes, we can take that back to 1900. And that is fairly certain because every single hurricane that hit land in America was recorded. Obviously, in 1900, they weren't recording them out in the Atlantic. They didn't have the technology, but they could record them when they hit landfall in America. So this is the landfall data from 1900 to present time. No change. No change at all. So there is no climate emergency in terms of hurricanes, tropical cyclones. Snow, you remember Dr. David Viner, again from the CRU, the biggest liars ever I think, in climate science by the sounds of it. Dr. David Viner said that our children will not know what snow is because of global warming. This was back in the year 2000, he said this. No change. This is winter Northern Hemisphere snow extent. No change. This comes from Rutger's Snow Lab. Again, this is the go-to source for all of this data. There it is up the top, Rutger's Snow Lab. No change in winter hemisphere snow extent. The only thing that has been happening is the snow has been melting slightly earlier. That's the only thing that has been happening with snow. You remember polar bears? The whole of this really started with the polar bears. Save the polar bear. The polar bears are going extinct. We've all got to shed a tear for the polar bear.
But actually they are thriving.
Yes, and here's the data. So this is Dr. Susan Crockford, and from 1960 up to present time, numbers have quadrupled. So not just surviving, but they've quadrupled in number. Yes, totally the opposite of what we were told. And sea ice, well, there was a big scare on sea ice. So the top is Antarctic, not much change until now. It was increasing for 35 years in the Antarctic sea ice, but now it's decreased a little bit. But the Arctic was decreasing. That was the big scare. All of the ice will go. I'm not sure why it was a big scare. Anyway, they made it into a big scare. But there's been no change in Arctic sea ice for 15 years. Since 2006. More than 15 years now. So yeah, no change in the Arctic for quite some time. The other thing it might be worth talking about is CO2, the radiation spectrum for CO2. There is something they don't talk about with CO2 very often, which is it has saturation, which means that the more CO2 we get, the less the effect it has. So CO2 is a greenhouse gas. I'm not claiming it's not. It does warm the surface by trapping heat in the atmosphere, like putting a blanket over the Earth. But its effect decreases. So this is a spectrum of the radiation that is coming back down to us from the sky. So the heat is trapped in the atmosphere, and the atmosphere re-radiates it back to the ground. And this is a plot of all the radiation that comes back down again. Now, without CO2, we follow the black line. And so all of this is radiation coming back down again. But then there's this sudden drop here, this tooth in the graph where it comes down, where none of that is radiating down. So there's a big gap there. And then it goes back up again. There's a gap there, and there it goes. So that's if there was no CO2. Am I saying that correct? No. So exactly what I said there, but without CO2, we follow the green line. Now, the green line is almost the same as the black line. It doesn't really show it, so that makes it more confusing. So without CO2, it's the green line here.
Mm-hmm.
Once we get CO2, we get this big drop. So this is extra radiation coming down from the atmosphere. This is up to 400 parts per million. So that's what we've got now. So suddenly, all of this area here between the green line and the black line, that is the extra warming we are getting from CO2. So it does provide quite a lot of extra warming, this CO2 in the atmosphere. But the thing is, when we increase beyond 400 parts per million, which is the red, so you can see here, the red is up to 800 parts per million, it makes no difference. So now we're looking for the change between the black line and the red line. And you see there's a little sliver here, and there's a little sliver here. That's the extra radiation we would get going from 400 parts per million to 800 parts per million. So almost nothing in comparison with what we had before. And what we had before is the difference between the green line and the black line, which was a huge area, all of this area. So what that means is as we increase CO2 from now on, the greenhouse effect of CO2 is virtually nothing.
Mm.
And that's another reason that they're now complaining about methane, of course, because CO2 is saturated. It's having less and less effect. So that's worth keeping in mind, in the back of your mind. This is another one just before we go off this. They were complaining that forest fires are increasing due to CO2. That's, the big tragedy. It's wiping out towns, forests, animals are dying because of forest fires. Well, this is the American forest fire burn acreage since 1926. Again, it's quite easy to monitor that. So this is a fairly good graph with good information. This comes from the NIFC, the Fire Information Statistics from America. And as you can see, back in 1926, this is the 1930s, there were many more fires than there are now.
Yeah.
So yeah, forest fires are not increasing. Well, a little bit increasing at the end, but nowhere near in comparison with the 1930s. The main reason for all of this is not the weather. It's because of what Trump actually said. And of course, they all jumped up and down and laughed at Trump. It was forest management.
Yeah, exactly.
Not due to weather. So what they had, the reason for this sudden drop-off was the 1930s crash. So we had the banking crisis in whenever it was, 1928 or something, or no, it was earlier than that, 24 or something. Anyway, the great stock market crash in America. and there were millions of people unemployed. So the government paid these people to go and do forest management just to keep them employed. And so there was a huge amount of forest management went on in the 1920s, and that brought the number of fires down very dramatically. Um, and in Europe, because they were complaining about forest fires in Europe very recently, this is from 1960. Is that 60 or 80? 1980 up to
1980.
2020, so 40 years. Forest fires in Europe are not increasing. So each one of these is a different country. We've got Portugal, Spain, France, Italy, Greece,
Mhm.
and which are the Mediterranean countries. That's where we get the forest fires. And yeah, none of those are increasing due to global warming. And the other thing they keep on about, of course, is we're all going to starve because agriculture is going to be stopped. Well, no, the only thing that's stopping agriculture at present is the EU, which keeps putting roadblocks in the front of farmers, which is why we have all of those protests in Holland and so on. I don't know if you've had protests in
Oh yeah, big
Germany.
ones.
You've
Mm.
had big ones too, yeah. That's what's going to reduce agricultural output, not climate. These are the stats for different crops. This is worldwide. This is global, and this comes from the UN. This is UN data. This is so cereals is the main one. That's the red one. Is going up. Sugar's gone down a little bit, but that's mainly due to taste. We're not eating as much sugar as we used to. All of these other crops are going up. Oil, vegetables, roots, and fruit, they're all going up. There is no crisis in agriculture other than um, governments getting in the way of farmers doing their job, which we've got the same in Britain as well.
A couple of weeks ago, there was a study published, and it turned out that plants actually store 31% more of CO2 than previously thought.
Yes, yeah, that's worth pointing out. I did have a graph somewhere of that. Um, NASA did a study of the greening of the Earth. So, because of the extra CO2 is actually allowing us to grow more crops. And they say that the amount of, I think in that study, it said the amount of increasing crops due to CO2 alone is 20%. But you're saying you saw one that said 30%.
Yeah, 31
Yeah,
or 32%, or
wouldn't be surprised.
around
Yeah.
that. Yeah. Mm.
So extra CO2 in the atmosphere is now feeding 1.5 billion people.
Mm.
So if we took the CO2 out of the atmosphere, which they want to do, we would actually head towards famine because
Yeah.
CO2 is plant food. We can't do without it. So the more CO2, the better. As people like I think it was William Happer, Professor Happer, and other people were saying, we are in a CO2 drought. We need more CO2 for food security. Otherwise, everything dies. Without CO2, all life on Earth will die, apart from mushrooms. But even they will die eventually because mushrooms don't need CO2 and sunlight, of course. And we'll see why that's a problem in a minute because that comes into my climate paper. So if I stop share and go into my second load of images. So if I load those up, share screen, and go to that one, I think. Yes, that one, and share that. Okay, so we're back to my climate paper. And this paper is quite famous now. It's had 45,000 downloads, which is quite a lot for a paper. A lot of papers only get a few hundred downloads at most because effectively, we're putting out too many papers. There are thousands and thousands of papers every year coming out, and most of them are totally ignored by the entire scientific community. So what's the point of doing all of this research if no one is reading these papers? There's just too many out there, and very few get exposure. This one has had exposure because I've advertised it, and it's had thousands and thousands of downloads. So it's been fairly influential. The reason I made this paper, as I mentioned before, is that there was no explanations for why the ice age cycle happens. There were theories, and there's various things we know are influencing the climate during ice ages, but no one could explain why we have ice ages. I'm just shutting my door because I've got a cold draft. So this is Professor Best made this graph for me. This is all of the different parameters that control climate for ice ages, and we're going to have a look at some of those. I think it's just a nice graph. It looks very good. The main one we want to look at is this one, because if people are not familiar with ice ages, this one gives us all the information we need. So along the bottom, today's date on the right, going back 800,000 years. This all comes from ice cores, by the way. We've got 800,000 years of ice core data from Antarctica. I used the Epica one, which is the EU drilling. They did this series of drilling holes in the ice, and it's called Epica. Temperature here in red, and CO2 on the right in blue. And as you can see, temperature and CO2 go up and down together. And of course, from that, people will say, well, CO2 is controlling temperature. No, because correlation does not equate to causation, of course. The reason they go up and down together is because of oceanic outgassing, solubility of the oceans. So the warmer the seas get, the less CO2 they can hold. So they give it out to the atmosphere. The colder the seas get, the more CO2 they can hold, and therefore CO2 levels go down because the CO2 goes into the sea. And that's why CO2 goes up and down with temperature. That's the main reason. So it's consequential, not causal. But it's worth remembering that CO2 and temperature do go up and down together. But that does not mean that CO2 is controlling temperature. And we know this, although some scientists will still say that, the feedback agent controlling ice ages, it's got to be CO2 because everything is CO2, isn't it? It's always CO2. It's the great god of the new climate religion. All hail to the great invisible God. But we know CO2 is not involved because, well, it is involved, but not in the way they think it is, because of this. So here we've got temperature again in red. So this time we've only got 450,000 years. So it's only half of the other graph. But nevertheless, 450,000 years, that's a long time ago. Red is temperature. Blue is the amount of sunlight hitting the northern hemisphere. Insolation, we call it, because sometimes I use that phrase, insolation, sunlight. And that's being controlled by orbital cycles. Now, we don't need to know very much about these orbital cycles, but you've got 3 cycles. You've got eccentricity, obliquity, and precession. And if you mix all of those together, you end up with this blue cycle, which is known as the Milankovitch cycle. So they effectively, it's just the orientation of the Earth and how close the Earth is to the sun, how elliptical the orbit is, how much the Earth is leaning. Sometimes it leans more than it does. Precession is the wobble of the Earth, so it wobbles like a gyroscope. So how much it is wobbling, that changes. And all of those things change the amount of sunlight that hits the northern hemisphere and the southern, of course, but in opposition. And you end up with this blue line. So the top of the blue line is extra summer heating in the northern hemisphere. The bottom of the blue line is less summer heating in the northern hemisphere, and the opposite in the southern hemisphere, of course. And as you can see, temperature is correlated, highly correlated, with Milankovitch cycles. I call these great years because I think great year explains it much better than Milankovitch. A great year is exactly the same as a normal year, except it's 23,000 years long. That's why it's known as the Great Year. So during a great summer, and this will be a great summer at the top here, marked in orange, during a great summer, we will have extra summer heating in the northern hemisphere, but extra cooling in the southern hemisphere during their summer. So it works very much like a normal year, except it's 23,000 years long. It's the great year, the great summer, the great winter. And we can see that the great summer here is correlated with warming. Not surprisingly, really. This warming is measured in the northern hemisphere, by the way, mostly. This is correlated with I suppose it's global. But we'll see why it's mainly correlated with the northern hemisphere. Anyway, you see it here, correlation between a great summer and temperature in the northern hemisphere. So that's one reason why we know that orbital cycles are involved in warming. And they say that the orbital cycle has a feedback, a terrestrial feedback, which is CO2, which helps the warming because they need, for many reasons, they need a terrestrial feedback. And that's the feedback, you see. As you get warmer, you get more CO2, and therefore more CO2 gives extra warming. And so CO2 is the feedback. But that doesn't make any sense.
I thought that CO2 gets more after the warming.
Yeah, it does by 700 years.
Yeah.
So that's one of the problems, that temperature leads CO2 by 700 years. So we get the warming before the CO2. And that means that CO2 is a very poor feedback. How can it feed back when it's happening later? That is a big hole in their theory. The other hole in their theory is that when we look at the top here, when CO2 is at a maximum, the world cools. And when CO2 is at a minimum, the world warms. So how can CO2 be doing this? CO2 is being a warming agent. So why does CO2 warm when it is at a minimum? And why does CO2 cool when it is at a maximum? It doesn't make sense. It's the wrong way round if you look at it like that. And we know that CO2 is not involved because this is, well, we've seen that graph. This is where we see the correlation between orbital cycles and temperature. Well, now let's look at this graph. Same graph, I've just highlighted different points on it. So now all of the purple ones are indicating the great summers, the orbital cycles, the Milankovitch cycles, which do not initiate warming. Mm-hmm. So all of these, we have very, very strong, great summers, lots of heating in the northern hemisphere, but no temperature response. Sometimes no temperature response. Here we got a little blip here, but sometimes we get no temperature response at all. So how can that be? Well, the first thing we know is that this is not just orbital cycles. So a great summer will not give us an interglacial warming. It needs a feedback system. So we know that we need a feedback system. Furthermore, we know that this feedback system is based in the Northern Hemisphere because all of these interglacials, here's a proper interglacial, they only happen in Northern Hemisphere great summers. They never happen in Southern Hemisphere great summers, which are displaced by 11.5 thousand years. And they just don't happen at that time. So this is a Northern Hemisphere phenomena. So it cannot be CO2 because CO2 is a global gas. If it was CO2 was the feedback agent, then we would get interglacials on both Northern Hemisphere warming and Southern Hemisphere warming. And we don't. We only get it on Northern Hemisphere warming. So we need a feedback that is Northern Hemisphere based. How can we have that? Well, we can, and we'll come on to that. Just looking for the next graph. Some people say it's obliquity. I won't go into this very much, but we have the same problem with obliquity. So if we separate out obliquity from the Milankovitch cycle, obliquity is just the leaning angle of the Earth, how much it leans. It actually changes quite a lot. It goes from about 22.5 degrees to about 24.5. It's about 2 degrees of difference, the amount the Earth leans over 40,000 years. So it's a 40,000 year cycle. So in this graph, we've got temperature in red going back 400,000 years, and the obliquity angle, I think it's measured in radians. So you'd have to calculate that in radians, in blue. And you can see we've got a nice cycle, goes up and down again. And some of these obliquity maxima are equated with warming in red. But we have the same problem because many of them are not. So all of these purple ones, we have obliquity maxima and no warming at all. So things like this one. So maximum obliquity and no warming at all. Same here. So it's not obliquity on its own. That one is stone dead, that one. We have this missing cycle problem. How can we have a cycle that only operates sometimes and it will skip 2 or 3 cycles and then happen again? How can that ever happen? Surely if you have a cycle, it follows the cycle. It doesn't sputter and stutter and only happen once every 3 cycles. Well, it can, but there is another thing that's involved, and that is dust. And nobody really looked at dust before I did. This is all my original research. We had people like Ganopolsky was saying, oh, there is dust on the ice sheets, and it was caused by the ice sheets grinding up the ground and making dust. No, this dust has been isotopically analyzed, and it comes from the Gobi. It doesn't come from the ice sheets. So we have Gobi dust on the ice sheets. And dust on ice sheets is important because that's exactly what we've got now, which may be causal to some of the warming we've got now. This is the Arctic ice sheet, and it's not as pristine as you might think. This comes from the Dark Snow Project, which was a project to study whether the darkening of the ice sheets by industrial dust, this is Chinese industrial dust on the ice sheets, whether that is affecting climate. Because obviously if you darken the ice sheets, they're going to warm up with the sun on them and they're going to melt much quicker. And the ice sheets are not very pristine, some of them. And that's this is the Arctic, that could well be affecting our climate. But we had dust back in the past as well. And here's a graph of that. So on the top is temperature. On the bottom is dust, again measured from the ice cores, coring the ice. And you can actually see the dust in the ice. And it's difficult to see on this, but we've got another graph coming up in a minute. There is a bit of a correlation here between dust and temperature. When temperature is low, dust is high. When temperature is high, dust is low. And that happens all the way along. This one is shaded where there is high dust. It's shaded. And obviously the shading equates to low temperature on each occasion. So there is a correlation here, but between dust and temperature. And this is another way of drawing that. We've got dust and CO2. Remember, CO2 is proportional to temperature. And the scatter plot gives a very, very nice scatter with a correlation between dust and CO2, and therefore between dust and temperature. And this dust comes off the Gobi. Here's the Gobi. Now today, if you go there, it's not, we call it the Gobi Desert, but it's not a desert. It's steppe grassland, the most of it. So it's covered in grass and animals and so on. It's sort of where Genghis Khan came from, I suppose, that sort of region. And here is the precipitation. And you see it's much less precipitation in the south, more precipitation in the north. And as I say, it's steppe grassland. And but if we go back to this, shall we have a look at one of the other graphs before we go to that? If we go back to the first graph, you'll see that CO2, which is in blue, comes way down during the Ice Age. So it comes down to 190 here. It's almost 180 parts per million. Now the death zone starts, for all plants, the death zone starts at 190 parts per million. So we nearly destroyed the Earth itself nearly destroyed all life on Earth, nearly died during the last Ice Age because CO2 came down so low that all plants were in danger of dying. And of course, if all the plants die, then all of the animals die. So we nearly lost the entire biosphere. All life on Earth nearly died during the last Ice Age because CO2 came down so low. And that's a problem because, as we've seen before, less CO2 and the plants die. And it's even more of a problem up on the Gobi because the Gobi is quite high. It's a plateau. We're up at 2,000 foot. And relatively up at 2,000 foot, there is even less CO2 because the partial pressure is less as we go up. Unlike one of my peer reviewers at the Royal Society who didn't understand that. How a scientist can't understand that as you go up in the air, you have less oxygen, and therefore, if you're a plant, you have less CO2. And so, well, you as air stewardess would know all about it. So I replied, why do we have emergency oxygen in aircraft then? If he was saying that the amount of gases remains the same with altitude. Okay.
No, certainly not.
So why do we have emergency oxygen then in our aircraft? I couldn't understand that one. That was a mad response. Anyway, so the problem is that the higher we go, we get even less CO2 proportionately in partial pressures. And so on the Gobi Plateau during the last Ice Age, there was insufficient CO2 for plants to grow. And so the whole of this Gobi region ended up as a CO2 desert, a brand new CO2 desert. Not a precipitation desert because the precipitation, and we'll see that in a minute, did not change that much. In fact, it got a slightly wetter, if anything. So it wasn't a normal precipitation desert. It was a CO2 desert. And the climate evangelists hate that term, CO2 desert. it shows us that, CO2 is important. If we don't have enough, we end up with deserts all over the place. And that's what we ended up with. A big desert across the whole of the Gobi, throwing dust all over the northern ice sheets, all over the Laurentide ice sheets, and the Euro-Asian ice sheets were covered in dust. And we can map that because, well, let's have a look at this first. Here it is. It's still there. So this is up in Greenland, where some of this ice still exists. So in Greenland, it falls obviously on Greenland and goes down, down, down through the layers, and then it spreads out. It's like treacle flowing outwards. That's the sort of consistency of the ice. In fact, I've got a lovely picture down here. I might as well show it now since we're looking at this. This is from Antarctica, looking a cross section, radar cross section, going down through the ice. And the ice here is flowing from right to left. And as you can see, it flows just like water over rocks or the atmosphere over mountains. And here it hits a rise and it just goes up and down, just like water would going down a fast flowing river. But it just does so very slowly. You can imagine how slowly this ice is flowing. I don't know how far it is. It's probably something like, I don't know, a kilometer every 10,000 years or something. I don't know how long it takes. I'll have to work that out at some point. It's like very, very thick treacle flowing across Greenland. And this is where it's come out at the edge of Greenland. And this is the dust. This is the Ice Age dust. So at the peak of the Ice Age, we had loads and loads of dust coming off the Gobi, which formed the Loess Plateau in China, this big dust bowl they have up in China. And here it is on the ice. And we can put some notation on there as well. So here's the dust in blue. Here's the dust of the Ice Age. And then, so this goes all the way up so this is from like 50,000 years ago, all the way up to about 15,000 years ago, when we had the interglacial warming. So the interglacial warming came and the dust stopped. That's why we get this white stripe here. The dust stopped because of the warming. Well, not because of the warming, it stopped because of extra CO2. Extra CO2 allowed the plants to grow back again. And so there was less dust. And then it came back again. You see another stripe here. This was the Younger Dryas. So it got cold again during the Younger Dryas, and all the plants died yet again. And so we got more dust. And that's why we get these two stripes here. So we can actually see this dust in situ still in Greenland. But we can also measure it when we core through Greenland. This core is actually again from Epica. So this is from Antarctica. The reason we tend to use Antarctica, you can use NGRIP, which is the Greenland one, but Greenland only has about 100,000 years of ice. Just because Greenland melts more. Antarctica never melts, and so we've got nearly 1 million years of ice in Antarctica. That's why we tend to use Antarctic ice. So this is a plot, and this is the money plot. This is the whole essence of my paper here. So at the bottom, we've got 0 to 800,000 years ago. On the right, we've got dust, and I've inverted dust here and made it logarithmic just to reduce the peaks down because the peaks were far too high. And on the left, we've got CO2. And remember, CO2 is proportional to temperature. So this equates to temperature as well. And as you see, there is a perfect match. You will not find a better perfect match between two data sets. CO2 is proportional to inverse log dust. There is a perfect correlation between dust and CO2. Why? Well, because This time it's causal, and there are many reasons for thinking this is causal rather than just sheer correlation. It's causal because the dust is causing temperature change, and the temperature change causes CO2 change because of the outgassing of CO2 from the oceans, because it's ocean solubility. That's why temperature and CO2 follow each other exactly, as we saw before. But the causal factor here is the dust. So what are we doing here? Well, let's look at this one, for instance. So 150,000 years ago, this was the depth of the ice age, and CO2 came down to the death zone,
Mm.
190 parts per million. And so yeah, so yes, because it's inverted. Okay. Um, I'm even confusing myself now. So here we're getting lots and lots of dust because the plot is reversed, of course, it's inverted. So as we come down to 190 parts per million, we get lots and lots of CO2. It goes up to 1,000, from tens up here, 10 and 20, it goes up to nearly 2,000. So an awful lot of dust is coming off the Gobi Plateau here. And then as soon as it starts to warm, the dust disappears. Why? Because the plants can now grow, because we've got extra CO2. Well, let's get this right first. Because we've got dust on the ice sheets. Dust on the ice sheets causes warming because it absorbs more insolation from the sun. That warms the temperature. That warms the seas. The seas can then outgas. The seas outgas more CO2, so the amount of CO2 goes up. And as soon as the CO2 goes up, then plants can grow on the Gobi Plateau again, and that cuts off the dust. And that's why dust just disappears all of a sudden during the interglacial. There is no dust. So it is the dust that is controlling the temperature and the CO2.
Mm-hmm.
Not CO2 is the controlling agent. The controlling agent is dust. Although CO2 is controlling this in some fashion, because it only happens because CO2 gets so low that all of the plants die on the Gobi Plateau. That's the only reason we get the dust. So conversely to what we're told, CO2 causes warming by getting too low. Not by getting too high, it's low CO2 that causes warming, because low CO2 kills all the plants, gives us loads of dust, and it's the dust getting onto the ice sheets that causes the warming. And that's why we have such a strong correlation here, because the true feedback agent that is controlling our temperatures during the ice ages is dust on ice. But of course, that could be part of the reason we have warming now. There is no direct evidence that CO2 is the warming. Well, there's a little bit of evidence from the tropospheric temperatures have warmed very slightly. But the tropospheric temperatures have not warmed as much as they expected for the greenhouse warming to be the cause of all the warming. Obviously, to get greenhouse warming, you need warming in the troposphere. That's where the greenhouse warming happens. And it was predicted that a certain amount of warming would be required by greenhouse gases in order to warm the surface. That's not happening as expected by a long way. It's something like only 1/3 of the warming that was expected has been observed by measuring the troposphere. And that's always been a problem for the climate scientists who are insistent that greenhouse warming is the only agent, because we're not getting enough warming out of the troposphere.
Mm-hmm.
In which case, some of the warming might be coming from somewhere else, and that other somewhere else may well be Chinese industrial dust on the northern ice sheets, darkening the ice sheets as we saw in those previous images. That might be the other source of warming that we've experienced over the last 30 years. Because remember, Chinese industrial dust has only really come about in the last 30 years or so with the industrialization of China. That's a fairly recent phenomenon, and it is perfectly in correlation with the warming we've experienced. So the warming we have experienced, which is not as bad as they expect, I'm estimating a third of the warming we've had is by temperature manipulation, you might say. There's been a lot of fiddling of the data, and a lot of that fiddling looks very, very suspicious. They keep changing the data records, supposedly for good reasons. They call it homogenization, because measuring stations change site, different instrumentation, different time of observation. That was a big change, the time they actually observe the temperatures. So there's been lots of changes, and they have to make allowances for it. But
I,
it's, yep.
I read an article recently. I'm not quite sure. I think it was the UK, and the article said that so many stations that are supposed to collect data and send it somewhere, they are all offline. They are doing nothing.
They don't exist. Yeah, they call them the ghost stations.
Yeah.
So a third of the measuring stations from the British uh, temperature sensing network don't exist. It's not that they're not transmitting, they're just not there anymore.
Okay. Yeah.
And yeah, ghost stations. And so what they've done is they've triangulated from other stations to say what the temperature there would be. But it's not there. You're not measuring anything.
So
Why on
that
earth
is
you?
guessing.
Yes, yeah, they're just guessing. Yes.
Okay.
Why on earth keep it going when you know it's been closed down and it's not there anymore? And a third of the stations are ghost stations. It's just incredible. Yes. So some of our, I think a third of our, oh yes, with the temperature measuring, they make all of these adjustments, but every single adjustment they've made has made recent temperatures warmer and past temperatures cooler. So you can start off with a graph that looks nice and flat, and by the time they finished adjusting it, suddenly we get a temperature increase out of it, merely through temperature adjustments. And you have to ask yourself, why does every adjustment make things warmer? That's why it looks crooked. So we've got a third of our temperature rise is by temperature manipulation, a third by greenhouse warming, and I think probably a third from dust on northern ice sheets. And that will have an effect. I mean, it did have an effect during the ice ages. We know it did. We can see it here. And it's a very large effect as well. You see, the other problem with the classical explanation for ice ages is that the CO2 effect is very weak. So over the 5,000 years, we get from 190 to 290, we get 100 parts per million extra CO2 since the depth of the ice age. That's how much it's gone up. And they equate that to about 4 watts per square meter of actual greenhouse warming that is warming the ground, warming the atmosphere. 4 watts per square meter. And they say that's sufficient. We've got 4 watts per square meter. And I keep saying to them, no, you haven't. That 4 watts per square meter is over 5,000 years. But that's not how warming works. Warming starts at 0 and goes century by century, not by a complete 5,000 years at the same time. So if we've got 4 watts per square meter, divided by 5, It's more like about 0.008
Hmm.
watts per square meter per decade. But we need to go from decade to decade. We can't just assume the 5,000 years. We've got to go from this decade, 5,000 years ago, to the next decade, and then the next one, and then the next one. Each time incrementally going up little by little. But the amount of warming we're getting from CO2 is only 0.008 watts per square meter. It's less than a bee in flight. And I don't think that's going to warm the atmosphere enough to go to the next stage, as it were.
Hmm.
But in this table here, this is warming by dust, changing the albedo, the reflectivity of the ice, how light or dark the ice is. We call that albedo. And if we change the albedo by 0.6, that's like 60%, we get 135 watts per square meter. If we change it to 0.5, so half change in the albedo from full albedo to no albedo. Because remember, bright white ice is something like 0.95 albedo. It's very, very bright. It reflects everything away. So all of that energy coming in from the sun during a Arctic summer, all of that energy is being reflected away completely. And remember, the ice sheets came all the way down to, in Britain, they came down to sort of Manchester in Britain. In America, they came down almost to Washington, New York sort of way. So they came down quite a long way. All of that area north of that was reflecting away all of the energy. No wonder it makes the earth cooler when you get so much reflection of energy. Put some dust on that. So if you go from 0.95 albedo down to 0.5 albedo, which is this line here, so we're reducing the reflectivity of the ice by quite a lot. Suddenly, we get 180 watts per square meter. So not 0.008 watts per square meter, but 180 watts per square meter every year. And they actually said to me, well, yeah, but that's only regionally. That's not globally. And I said, well, yes, but when you have winter snow in Canada, it's not the temperature in Argentina that melts that snow. It's the regional effects in Canada itself that will melt that winter snow. The reflectivity of the ice. If you get dirty ice at the side of the road, it will melt quicker than normal ice out on a farm or something. And so here, when measured regionally in the Northern Hemisphere, we're getting 180 watts per square meter every summer, which is obviously the melting. The winter is irrelevant because there is no melting in the winter anyway. But every summer we get 180 watts per square meter extra energy being absorbed by the ice. No wonder it melts. So the strongest feedback agent we possibly have for interglacial warming and melting is dust on ice. It's not CO2. And so that is the essence of this theory, that the scientists have got this all backwards. CO2 is not the primary feedback agent. It just doesn't make any sense. The primary feedback is actually dust on ice. And that has some knock-on effects. It means that the runaway effect that they keep talking about does not exist, because the runaway tipping feedback with CO2 is that if you get more and more CO2, it can carry on warming. Well, that's not true, because the effects of CO2, as we've seen, drop off as we increase CO2 with saturation. So that's not true for that reason. And it's certainly not true if the feedback agent is dust on ice, because the feedback system stops when we have no more ice during the summer in the Northern Hemisphere. The feedback then stops at that point. So there is a limit beyond which the temperature won't go. And that's sort of what we see in these graphs where they all top off at the same level. Now, why did that happen? Well, because there is a natural limit to the amount of warming we can get from dust on ice sheets. And that's when the dust, when the ice sheets become so small that they're no longer having an effect on climate. So there's a natural limit to the amount of warming. And the other thing is that, of course, we know how to stop ice ages, because if we look at this one, here we are now. We're still in this interglacial era here, and the amount of warming through orbital cycles, the Great Summer, the amount of warming is decreasing. We are supposed to be going into a new ice age. That's why they had the scare in the 1970s about, oh, the new ice age is coming.
Yeah. I remember that.
Yeah, they changed it into warming very quickly, didn't they?
Mm.
That was a bit premature because, in my estimation, it's not going to happen for about another 500 or 1,000 years.
Mm.
And also, this, because it only happens with a great winter. And this great winter we're coming up to now is a very shallow one. So you can see some of them go right down here. And that really does make it cold in the northern hemisphere. Same with this one. And so you get immediate cooling. And you can see the red line going down very rapidly. So you get immediate cooling straight into another ice age from which it never recovers. So this idea that you get a sudden warming and then a very slow cooling into the ice age is a bit of a nonsense, really. You can see on this graph, we get an interglacial, goes up, and then the cooling is very rapid into the next ice age. And then we get subsequent cooling after that. But the initial cooling is very, very rapid. So you can drop into an ice age very quickly. But ours is extended because we are in a low eccentricity position at present. I don't have the eccentricity graph on here. When we have low eccentricity, the precessional component of the warming is very low. And we're mainly reliant on obliquity, the tilt angle of the Earth. And because of that, we don't get very deep great winters. And we can see the same here. 400,000 years ago, eccentricity was low, and therefore we didn't have any great summers or very strong great winters. You can see here the great winter bottomed out at this level. Instead of these ones, went all the way down here. They were much stronger. And so you get this big extended interglacial, and you can see the extended interglacial here because the obliquity cycle is 40,000 years long. And we've got exactly the same here. We've got this extended interglacial, not like these, which are straight up and straight down. And that's because eccentricity is low, which means the next great summer is not going to be very deep. So we're not entirely sure if it's going to be strong enough to drop us into an ice age.
Mm.
But even if it does, we know how to stop them now. It's dead easy. We could do it tomorrow. All you need to do is get some spray equipment onto 747s or A380s and just spray the ice sheets with, well, not dust. The best is soot, carbon soot. So just spray the ice sheets with soot and you'll stop the next ice age, because ice ages are controlled by dust on ice. And soot on ice is even better than dust. Soot is about the best absorber you can possibly get. So we can stop the next ice age very easily, no problem at all. So we have no worries about the next ice age. And this this low eccentricity carries on for about another 70,000 years. So we're in a very benign era orbitally for the Earth. We don't come across another strong great winter for about 70, 80,000 years. So yeah, we're fairly well off at present. Here, we would have struggled, I think, to stop this ice age coming in. It was so much colder. You can see, and this is in watts per square meter. They're talking about CO2 changing the strength of the sunlight by 4 watts per square meter. Yeah, that's all the way from 190 parts per million up to 200, up to 300 parts per million. 4 watts per square meter. In fact, no, it's more than that because it's a doubling of CO2. So that would be from call it 190 all the way to 400 parts per million would be 4 watts per square meter. Well, here is the watts per square meter, and the warming potential of this great summer goes from down here, say, from 440 watts to 540 watts, a whole 100 watts per square meter of extra warming. And CO2 as a feedback agent is only going to produce 4. You can see how weak it is in comparison. So yeah, you'd have to do quite a lot to prevent that ice age starting there as the temperatures dropped off during the summer in the northern hemisphere. So that is the paper. That's what I've been up to, and it's caused a bit of a kerfuffle, to say the least. This is Greenland. I just put this in because it's interesting. People don't know about Greenland, perhaps, because you only see it with the ice on the top of it. This is Greenland without ice. And this is the reason we have a Greenland ice cap. Now, ordinarily, that ice cap shouldn't be there. It should have gone thousands of years ago. The reason the Greenland ice cap is there is because it's sitting in a big trough. Now, it's probably caused that trough itself because it's so heavy, basically. And so it can't slip off, which ice can do, of course. It can flow off if it's not trapped. Here, it's trapped by this ring of mountains, which means A, it can't slip off. B, the bottom of the ice sheet is not warmed by the sea. So the sea cannot undercut it as it did with the ice sheet that was sitting off, the Scandinavian coast and so on, the Baltic ice sheet and so on. That was warmed by the sea and it melted. All of the other ones across the north, they all melted, except for this one, because the sea cannot get to it. And the ice cannot easily run off into the Arctic Ocean. So that's Greenland. So I always think that's an interesting geological structure. And then on top of that, of course, it's 3 kilometers thick. Can you imagine 3,000 meters, 10,000 foot of ice on the top of it, way up here, big dome of ice. The other thing that my paper did is it changed all of the paleoclimate models, which they are still debating and so on, whether they're actually going to change them, because they're all wrong. And that's a problem. If you're trying to assess climate, how can you do so when your paleoclimate models are all completely wrong? Now, what they did is you need to assess what the temperature was in the past. Now, they do that through tree lines, and you can see a nice tree line here. And those tree lines are controlled by temperature, of course. The higher you go, it gets colder, and beyond a certain point, the trees won't grow, and you end up with a tree line. And that tree line, for a particular species of tree, will tell you exactly what the temperature is. So it's a pretty accurate way of seeing what the temperature is. And of course, you can see old tree lines in the ground. If you look around here, going up and down the mountain, you can see where the old tree line was. And from that, the old tree line will go down and down and down, of course, because it was colder back during the Ice Age. From that, you can tell how cold it was in the tropical regions. We can tell how cold it was in the Arctic regions because we've got the ice cores, and the ice cores will tell you how cold it was. They look at changes in the oxygen isotopes, and that will tell you the temperature in the Arctic and the Antarctic, but it won't tell you the temperature in the tropics. And so in the tropics, one of the ways of doing it is by tree lines. Trouble is, they were using temperature as the tree line modulator or operator, and it wasn't. What they didn't realize is that tree lines during the Ice Age were being modulated by CO2, and they've never looked at CO2 as a modulator before. Obviously, we've labored the point enough. If you don't have enough CO2, all of the plants die, especially these trees, which are all C3 trees, they call them, which are affected greatly by CO2. And so the tree line was being modulated by CO2, not temperature. And so they got the calculation for their temperatures completely wrong for the paleoclimate. And they ended up with these huge, great lapse rates, which made no sense whatsoever. I mean, the average dry lapse rate is something like 3 degrees per 1,000 foot. And they were ending up with like 4.5 degrees per 1,000 foot for a dry lapse rate, which is just nonsense. And so there was a lot of head scratching, and they fudged the figures, basically. If they'd known, they could have kept the lapse rate correct, adjusted the tree line according to CO2, and then they could have made the paleoclimate maps. So this is a paleoclimate map. I'm not sure when this is. I think this is peak of the Ice Age. This would be something like 25,000 years ago. And they're trying to map out the weather and the climate during the Ice Age. And this is precipitation. This is the amount of rainfall. And they're saying here the red is much, much less rainfall. So across the tropics, they've got no rainfall at all, hardly. It's really a lot less. Why? Well, because they've got the wrong lapse rate from the mountain tree lines. And so this red line here shouldn't exist at all. It wasn't drier at all during the Ice Age. There was probably not much difference. The Chinese debated this because they were saying that the Gobi Desert should be much drier. And the Chinese scientists were saying, well, the lakes look as though they were just as full as they are today. So we don't think that the climate was drier just because we were in an Ice Age. And so, yeah, these paleoclimate maps may need adjusting because of my research. So we'll see if they actually go ahead and do that. And that, I think, is about the end.
Yeah.
So I don't know if that all made sense.
Yeah, it made sense to me, definitely. So in other words, net zero is not a good idea. This was the public hour. For full access of the entire interview, please join our Patreon community. Thank you.